By 2040, the world will look dramatically different than as we know today due to numerous technological advancements. For example, 4D printing, which is an advanced additive manufacturing technique that can create complex structures, including human tissues and organs, can revolutionize the entire healthcare. Unlike traditional 3D printing, 4D printing enables the creation of structures that can self-assemble, adapt, or evolve after printing. 4D printing involves materials that can change shape, properties, or function over time in response to environmental stimuli like heat, light, or moisture. Potential uses include printing human tissues, organs, and implants that can grow, heal, or adjust to changes within the body, advancing regenerative medicine. 4D printing can produce adaptive products in various industries, such as self-repairing materials, responsive clothing, and adaptive building materials. The technology could lead to more efficient manufacturing processes with reduced waste, as materials can be programmed to optimize their function after printing. Fusion power might be the energy we will be using in 2040 and can be the answer to increasing of worldwide energy consumption. The fusion power generates energy by fusing atomic nuclei, a process similar to the one powering the sun, releasing immense amounts of energy. Fusion uses isotopes of hydrogen, such as deuterium and tritium, which are abundant in water and can provide a nearly limitless supply of fuel. The fusion process produces no greenhouse gases during operation, and its primary byproduct, helium, is harmless, making it a highly clean energy source. Unlike nuclear fission, fusion carries no risk of meltdown, and it generates minimal long-lived radioactive waste. Achieving and maintaining the extremely high temperatures and pressures required for fusion, as well as containing the reaction within a reactor, are today's major technical challenges. Projects like ITER, International Thermonuclear Experimental Reactor, are working to demonstrate the viability of fusion as a large-scale energy source. If realized, fusion power could provide a nearly inexhaustible and sustainable energy source, revolutionizing global energy systems and helping to address climate change. CRISPR, or clustered regularly interspaced short palindromic repeats, is a unique technology that enables geneticists and medical researchers to edit parts of the genome by removing, adding, or altering sections of the DNA sequence. Right now, it is the simplest, most versatile and precise method of genetic manipulation and is therefore causing a big buzz in the science world. CRISPR is being explored to correct mutations responsible for inherited diseases like cystic fibrosis, sickle cell anemia, and muscular dystrophy. The technology holds promise for preventing genetic diseases by editing embryos or germline cells, potentially eliminating hereditary conditions. CRISPR technology also has the potential to transform medicine, enabling us to not only treat but also prevent many diseases. We may even decide in the future to use it to change the genomes of our children. Carbon capture and storage, CCS, are the technologies designed to capture and store CO2 emissions, helping to combat climate change and global warming. CCS technologies can capture carbon dioxide emissions directly from industrial sources, such as power plants, before they reach the atmosphere. The captured CO2 is then transported, typically via pipelines, to storage sites or utilization facilities. CO2 is injected deep underground into geological formations, such as depleted oil fields or saline aquifers, where it can be securely stored for thousands of years. By preventing CO2 from entering the atmosphere, CCS helps reduce greenhouse gas emissions, playing a critical role in efforts to combat climate change. CCS is applicable to various industries, but it faces challenges including high costs, energy requirements, and the need for widespread infrastructure. As technology advances and costs decrease, CCS could become a key tool in achieving global carbon reduction targets and supporting a transition to a low-carbon economy. Advanced brain-computer interfaces, BCIs, are devices that allow the human brain to control external electronic devices by translating brain signals into commands. BCIs can be non-invasive, using external sensors like EEG caps, or invasive, involving implanted electrodes in the brain. Future generation BCIs will look like today's in-ear headsets or even smaller and will not require any invasive intervention. BCIs are used for restoring movement in paralyzed patients, enabling communication for those with severe disabilities, and treating neurological conditions. Potential future uses include cognitive enhancement, memory augmentation, and direct control of digital environments or robotic systems. Exoskeletons are wearable devices that augment human strength, endurance, and mobility, helping users lift heavy objects or walk long distances with ease. In industries like manufacturing, construction, and logistics, exoskeletons reduce physical strain on workers, increasing productivity and reducing injury risks. Exoskeletons are used in medical settings to assist patients with mobility impairments, helping them regain movement and improve rehabilitation outcomes. These suits can enhance the performance of soldiers or emergency responders, enabling them to carry heavy loads or operate in challenging environments. They range from full-body suits to partial devices that support specific body parts, such as the legs, arms, or back. The development of quantum computers, which will solve complex problems beyond the capabilities of classical computers. Quantum computers leverage the principles of quantum mechanics, using qubits that can represent and process multiple states simultaneously, unlike classical bits. These computers can perform complex calculations at speeds exponentially faster than classical computers, making them ideal for solving problems that are currently intractable. Quantum computing could accelerate advancements in fields like materials science, drug discovery, climate modeling, and artificial intelligence by processing vast amounts of data and simulating complex systems. These computers are particularly powerful in optimizing large-scale systems, such as logistics networks, financial portfolios, and energy grids. Quantum computing is still in its early stages, with significant technical challenges related to qubit stability, error correction, and scaling up the technology. As quantum computing matures, it could transform industries, solve some of the world's most complex problems, and lead to new scientific breakthroughs. Self-healing materials that can automatically repair themselves, extending the life of products and infrastructure. These materials have built-in properties that allow them to automatically repair damage, such as cracks or scratches, without human intervention. In construction, self-healing concrete and coatings can help maintain buildings, bridges, and roads by autonomously sealing cracks and preventing structural deterioration. Self-healing materials can be used in everyday items like smartphones, cars, and clothing, keeping them in good condition for longer periods. These materials may heal through chemical reactions, microcapsules releasing repair agents, or polymer chains reconnecting at the damage site. By reducing waste and maintenance costs, self-healing materials contribute to sustainability and economic efficiency in various industries. Nanotechnology research and development involves the design, creation, and manipulation of materials at the nanoscale, where properties can differ significantly from their bulk counterparts. Nanotechnology is used to create smaller, faster, and more efficient electronic components, such as transistors, sensors, and memory devices, driving the next generation of computing and communication technologies. Nanomaterials, like carbon nanotubes and graphene, offer superior strength, flexibility, and conductivity, leading to the development of lighter, stronger, and more durable products. In medicine, nanotechnology enables targeted drug delivery, early disease detection, and the development of advanced treatments like nanoscale surgeries or regenerative therapies. Nanotechnology can contribute to environmental protection by creating more efficient energy storage systems, water purification technologies, and pollution control methods. Nanotechnology is still at the beginning, but in the future is expected to revolutionize industries, leading to breakthroughs in healthcare, manufacturing, and sustainable technologies. Smart grids and wireless energy transfer is another important topic to be covered. Future smart grids utilize digital communication technologies to enhance the transmission and distribution of electricity, allowing for real-time monitoring and control. By employing advanced sensors and automated systems, smart grids can quickly identify and address outages or faults, improving the overall reliability of the electricity supply. Smart grids allow for dynamic demand response, enabling consumers to adjust their energy use based on real-time pricing and grid conditions, leading to more efficient energy consumption. The concept of smart grids promotes decentralized energy generation through microgrids and distributed energy resources, empowering communities to produce and manage their own energy. With smart meters and mobile applications, consumers will have greater visibility into their energy consumption patterns, allowing them to make informed decisions about their energy use and savings. Imagine that you can couple smart grids with wireless energy transfer, that allows electricity to be transmitted over distances without the need for physical connections, eliminating the need for cables. These techniques include inductive coupling, which are today used in wireless chargers, resonant inductive coupling, and microwave or laser-based transmission for longer distances. Wireless energy transfer technology can facilitate the charging of electric vehicles, EVs, without plugging in, enhancing user experience and supporting EV adoption. The technology can power streetlights, public transport, and smart devices in urban environments, contributing to the development of smart cities. In healthcare, it can provide power to implanted devices, like pacemakers and wireless sensors, improving patient safety and comfort. Efficiency, distance limitations, and safety concerns such as exposure to electromagnetic fields remain challenges that need to be addressed for widespread adoption in the future.